Okay, in this video I'm going to talk about how Gauss's law that we recall is that the charge enclosed by a surface is actually determined by the electric flux through that surface. And I'm just going to show that it actually works for a point charge. So in this case, we'll consider just a positive charge Q. And actually what I'm going to do is I'm just going to show it works for a sphere. You can show it works for every surface, but that's a little more messy. And this is a nice calculation that will hopefully convince you. So we'll just consider the sphere of radius A, and our electric field obviously is just by Coulomb's law, which is electric field is kq times the position vector divided by r cubed. Remember, this is just 1 over r squared if you take the magnitude. That's the original Coulomb's law. So what we'll do now is we'll evaluate that surface integral. We're going to evaluate that surface integral of E dot ds, and we're going to show it's going to equal to q divided by epsilon naught. Remember that k is 1 over 4 pi epsilon naught. That's what the physicists call that. And so that's where the epsilon naught is going to come in. And the 4 pi is actually going to show up with that surface integral. And so let's do this thing. So I think that spherical coordinates is the natural way to do this. Okay, and remember that ds is the normal vector times the area. So that normal vector is easy. Just by inspection, it should just be the position vector divided by its length. And the area, I've gone through this in a previous video. The heuristic is just to drop dr, or d rho, from the volume for spherical coordinates. So that means it should be rho squared sine phi d theta d phi. That's not a rigorous thing I just said, but it's a nice way to remember it, surely. So E dot ds, it'll be kq over r cubed, r dot with a bunch of stuff. So let's add that r over a here. And now we're going to add the ds at the end. Okay, so we have some cancellations to do. So this is an r squared, this is an r cubed, and r equals a. Oh, and I should say that this should be rho, I suppose. Let's just call it r, just to make things a little easier. So we ended with kq r squared over r cubed. We have that 1 over a, we have the a squared, and then we'll have more stuff, which I'll just pause. So all these r's, we end up with a4 divided by a4, so these cancel. And that's good, right? Because there's no a's on the left-hand side. Okay, so we end up with kq times sine phi d theta d phi. That is our integrand that we need to deal with. So the claim is that q over epsilon naught is the integral of kq sine phi d theta d phi. And we'll have our usual maximal spherical ranges. So if we do phi here, it'll go from 0 to pi. I'm just going to recall the range of phi for those who forgot about spherical coordinates. And theta will go from 0 to 2 pi. So now I'm just going to do the usual splitting. 0 to 2 pi of d theta, 0 to pi of sine phi d phi, and then a kq will come on the outside. This will be a 2, this will be a 2 pi, so we end up with kq times 4 pi. If we now recall that k is that 1 over 4 pi epsilon naught, we get exactly what we wanted. So Gauss's law works. And you didn't have to take my word for it. You could have taken Gauss's word for it. That should be worth a lot more. Thanks for watching.